Hey, guess what time it is, class? It's science time. Now take out your notes and let's get learning. So the second part is moles of a substance based on volume. And there's a new term here which is called STP. So STP stands for standard temperature and pressure. And standard temperature is 0 degrees Celsius, or anything that's going to be equal to 0 degrees Celsius, which is going to be 32 degrees Fahrenheit or 273 degrees Kelvin. But most often you're going to either hear 0 degrees Celsius or 273 Kelvin. Standard pressure is 1 atmosphere pressure, or anything equal to 1 atmosphere pressure. And that's 760 millimeters of mercury, which is also the same thing as 760 torrs, 101.3 kilopascals. PA stands for pascals, or 1.013 times 10 to the 5th pascals. So this would be the air pressure that you would have if you were at sea level. So in other words, if you're at sea level and the temperature is 32 degrees Fahrenheit, which is 0 degrees Celsius, the air will be described as being at STP. So we're looking at volumes of a gas. This does not pertain to volumes of a liquid. This does not work for volumes of liquids here. So the molar volume at STP, 1 mole of any gas occupies a space of 22.4 liters, which means it does not matter what type of gas that is. So if you were to go at sea level and 22.4 liters, that's almost 6 gallons of air. So in other words, if you were to have 6 empty containers of milk containers, and you were to go at sea level and uncap them and cap them back on here, and if the outside temperature was about 0 degrees Celsius, you would have 1 mole of gas captured total within those 6 gallons of empty jugs, which would mean you would have 6.022 times 10 to the 23rd gas particles within that, or 1 mole of gas particles. So if you had helium, and it's at 1 atmosphere pressure and at 0 degrees Celsius, you would have 1 mole of gas, of helium. If you had carbon dioxide, same thing with carbon dioxide. If it was oxygen, same thing with oxygen. Even if it's a mixture of gases, in other words, like our atmosphere is nitrogen, oxygen, some carbon dioxide, some argon, and some other stuff here. But if you just look at the gases, as long as they're at 1 atmosphere pressure and 0 degrees Celsius, or also what's referred to as STP, you would have 1 mole of gas. Now, some of you might be wondering, well, what happens if it's not that way? What if the pressure is either higher or lower, or the temperature is different? There are ways of figuring that stuff out. Those are called gas laws, and we will not be getting into that in this section. We'll probably end up, if you ever end up taking Chem 2, then we do get into gas laws, or also in advanced physics, we get into gas laws. So we look at what happens to gases when they're not at STP. But for now, all that you need to know is 1 mole of any gas occupies a space of 22.4 liters, which now is going to become another conversion unit of 1 mole of gas is equal to 22.4 liters at STP. One thing I would like for you to do is get your flowchart again, and just a little reminder that grams to moles, we need to use this conversion where X number of grams is equal to 1 mole. Periodic table, or the formula weight, is what's going to be used to determine what this X value is going to be. And then moles and number of particles, which could be atoms, molecules, ions, anything here. And 1 mole is equal to 6.022 times 10 to the 23rd particles. So what we're going to be doing now is we're going to be adding onto this flowchart. So from here, I'm going to add another line with liters, and this only applies to a gas at STP, standard temperature and pressure. So we're going to add one more branch to this flowchart. And this conversion that we're going to be using is this. I want you to write on here 22.4 liters is equal to 1 mole. So that's what we're going to be adding onto this flow chart, which again can mean 22.4 liters over 1 mole, or 1 mole all over 22.4 liters. Okay, so we just now added a new branch onto a flow chart. So if we're dealing with a gas and it's at STP, and we know the volume of the gas, the volume is measured in unit of liters, we can use this to determine how many moles do we have, and then the moles, we can figure out either how many particles do we have, or even what is the mass, how many grams is that. So the moles, as you can see here, is kind of the hub of figuring out most of the information about these compounds. So again, this only applies for gases, and they also have to be at STP. If it doesn't tell you for everything that we're going to be doing with this stuff here, assume the gas to be at STP. And this does not apply to volumes of liquids. What is the volume in liters of 0.6 moles of sulfur dioxide, which is SO2 gas at STP? Okay, we have 0.6 moles of SO2. Now, since we have 0.6 moles of sulfur dioxide, we want to know what is the volume. The volume is measured in liters. So we need to go from moles to liters. I need to be using this conversion unit here. So open up a set of parentheses. Now, since I have moles, I'm going to get a new pen here. All this is over 1. I got moles. 1 mole is equal to 22.4 liters. So moles is on top. I need to put moles on the bottom to cancel it out. And then on top, I'm going to have 22.4 liters. This way, moles will cancel out. So I'm going to take 0.6, technically divide by 1, it's going to give you the same number, times 22.4 divided by 1. So whenever you multiply and divide by 1, it's the same thing. So you always multiply the top, divide the bottom. So 0.6 times 22.4, and we end up getting a value of 13.44 liters of sulfur dioxide, SO2. So there's your answer. So if you have 0.6 moles of sulfur dioxide, you're going to have 13.44 liters of sulfur dioxide, SO2. Number 2, the density of a gaseous compound containing carbon and oxygen is 1.964 grams per liter at STP. Determine the molar mass of the compound. Number 2 is going to be a little bit different. You're going to find out the density. Now, this is something we had gone over a while back, and you have to look at the units of what are the units for formula weight, and what are the units for density. Now, for formula weight, or molecular weight, or whatever you want to call it here, units for that is a gram per mole. Density, looking at density, units for that, in this particular case, is grams per liter. If you remember, density is equal to mass divided by volume. Mass is measured in grams. Liters is a unit of volume. Now, sometimes it can be milliliters, sometimes it can be cubic centimeters, but in this case, we're going to be working with liters. So if you look at these two units, one thing you should see here is, first of all, the grams don't change. They both have the unit grams on top. The only thing that's different is the denominator, moles and liters. So formula weight is in grams per mole, density is a gram per liter. What we need to do is we need to get the unit moles into a unit of liters, or vice versa, depending upon which way you're going here. And this only applies to gases at STP. Are you able to do something like this? So the problem starts off where you have 1.964 grams per liter. Now, when it's written out like this, that is per 1 liter. So what we need to do is we need to get, and we want to know what is the formula weight for this compound, so or the molar mass of the compound. So we need to get we need to go from here to here. So really the only thing we have to switch is liters into moles. So we already have the unit liters. We need to get to the unit of moles. So we're going to have to use this conversion unit again. So if you look at the problem, now here's something else which is also going to be a little bit different. Unit liters is on the bottom. Now most often when we're working with stuff here, you know, we're starting with moles on top, moles on the bottom for this. But here, liters is on the bottom. I need to get rid of liters. So I need a unit of 22.4 liters on top, and then 1 mole on the bottom. And if you look at this, liters is on the bottom, liters on top, they cancel out. And if the units are left over, is a gram on top, moles on the bottom. That's what I want over here. I want grams on top, moles on the bottom. So you're going to take 1.964 divided by 1 times 22.4 divided by 1. And when you work this out, that comes out to be 43.9936 grams per mole. Technically it's per 1 mole. Or sometimes it's just written out as 43.9936 grams per mole. Either way. Now, even though it's not asking the question, because this is a gas and it's made up of carbon and oxygen, you can even figure out what the compound's going to be. It's either going to be carbon monoxide or carbon dioxide. And if you look at the weights between these two, 1 carbon, 1 oxygen. I'm just going to round the numbers here a little bit. 1 carbon, 1 oxygen. Carbon is roughly 12. Oxygen, 15.9994. I'm just going to round it to 16 just to make the math a little bit easier. This would have a formula weight of roughly 28 grams per mole. Carbon dioxide, carbon is about 12. And I have 2 oxygens. So that's like 16 plus 16, which is a total of 32. 32 plus 12, the total is 44 grams per mole. So from this, we can even determine that this gas is carbon dioxide, CO2. Just from that little bit of information here. So if it's a one type of gas, if you know what it's made up of, you can measure the volume of it. You can also measure the mass to figure out what is the density of it. And if it's a gas at STP, you can also figure out the formula weight for that compound, which can also be used to determine what is that compound. So one thing, this is one technique sometimes used to identify a substance. Assuming STP, how many moles are 0.88 liters of helium? We have 0.88 liters of helium. We want to know how many moles are there. So we're going from liters to moles. Again, we're going to be using this conversion unit here. So start with what's given to you. So you have 0.88 liters of helium. And then you need to figure out how many moles are there. Now, technically, this whole thing is over 1. And since this liters is on top here, I need liters on the bottom here. So I'm going to put 22.4 liters on the bottom and 1 mole on top. This way liters will cancel out. 0.88 divided by 22.4. So when you work that out, it comes out to be 0.0393 moles of helium. There's your answer there. So if you have 0.88 liters of helium, a little bit less than 1 liter of helium, as a gas at STP, this would be how many moles. So this is kind of like a grouping of helium. And if you need to, you can even take a step further and figure out how many individual atoms of helium do you have. Number 4, assuming STP, how many molecules are in 1,000 liters of C2H6, which is ethane. So we're looking at how many molecules are in 1,000 liters of ethane, which is C2H6. So if you have 1,000 liters of ethane, C2H6, we want to find out how many molecules are there. So if you look at the flow chart, we have 1,000 liters, so we're starting down here. We want to know how many molecules are there. We need to get here. So you first have to go from liters to moles, and then moles to number of molecules. Now if you look at this route right here, even though we're working with the compound C2H6, we don't need this information here. So this is one of the situations where we don't have to figure out the formula. If you did, that's fine, but it's not necessary in this situation. So first step, liters to moles. We don't want to use this conversion. So open this up. I have the liters already. So I'm going to put 22.4 liters on the bottom, 1 mole on top. Liters are going to cancel out. So 1,000 liters times 1 divided by 22.4 comes out to be 44.643 moles of ethane, C2H6. So go from liters to moles. So we have 44.643, so we're right here. So moles to number of molecules, we now need to use this conversion. So I'm going to rewrite this over here. 44.643 moles. Again, technically this whole thing is over 1. So moles is on top. I need a mole on the bottom. 1 mole on the bottom, and on top, 6.022 times 10 to the 23rd molecules. If you look, moles on top, moles on the bottom, they cancel out. So I'm going to take 44.643 times 6.022 times 10 to the 23rd, divided by 1, which comes out to be 2.6884 times 10. Now make sure if you put it in correctly, it should be to the 25th molecules. C2H6. So that's your answer for that part. So if you have 1,000 liters of ethane, we've figured out how many molecules of ethane and even how many moles of ethane. Number 5, carbon dioxide at STP has a volume of 10.8 liters. What is the mass of the carbon dioxide? CO2 at STP has a volume of 10.8 liters. So I'm going to start with 10.8 liters carbon dioxide. What is the mass of carbon dioxide? So we're starting going from liters to moles, and then from moles to grams. Now, as you can see here, we got to go through this part here, where we need to figure out the formula weight. Oops. We need to figure out the formula weights for the compound. So let's take care of that first. Now, carbon dioxide, if I have 1 mole of CO2, I'm going to have 2 moles, I'm going to have 1 mole of carbon and 2 moles of oxygen. All right, so we need to find out the weight of each one of those. So carbon is 12.011 grams for every 1 mole. Oxygen is 15.9994 grams for every 1 mole. So you get that information from the periodic table. So therefore you're going to have 12.011 0.11 grams of carbon, and then 31.9988 grams of oxygen. So the total mass of carbon dioxide is 44.0098 grams, is equal to 1 mole of CO2. So this right here is your X value. This is your X grams. All right, so let's continue on with the problem. So it starts off where you have 10.8 liters of CO2. So the first step is we need to go from liters to moles. So I needed to use this conversion unit. So this whole thing is over 1. Liters is on top. I need liters on the bottom, which is 22.4 liters on the bottom, 1 mole on top. This way liters can cancel out. So you're going to take 10.8 times 1 divided by 22.4, and you get 0.4821 moles of carbon dioxide. So now we're trying to find out how many grams, what is the mass of it. So we got the moles, 0.4821. Now I can go use that information to solve for how many grams do we have. But we need to use the formula weight, which is this up here. So let me rewrite this. 0.4821 moles of CO2. Since this is all over 1, I'll use this information up here. So 1 mole is on the bottom, and 44.0098 grams is on top. Moles are going to cancel out. So 0.4821 times 44.0098, we get a total mass of 21.219 grams of carbon dioxide. So that's your answer for that part. All right, this concludes the second part of the video. In the next part, we're going to get into percent composition.